Okay, good afternoon and welcome everyone. My name is Hisham Sadi. I'm a professor of mathematics and associate dean of science here at NYULD. We are happy to see you all at this event that is jointly between the Division of Science at NYULD and ADIA Lab as part of a wider collaboration between the two institutions. We are very honored this evening to have the lecture by our distinguished speaker, who will be introduced by the director of ADIA Lab, Dr. Horst Simon. So in turn, it's a big pleasure for me to introduce Horst. So prior to joining ADIA Lab as an inaugural director in 2022, Dr. Simon was at Berkeley Lab from 1996, having served previously as deputy director for research, associate laboratory director for computing sciences, and director at NERSC. It's a pleasure to be working with you, Horst.
Good afternoon. It's always a great pleasure to be here at NYU, and I would like to thank Hisham and our colleagues at NYU Abu Dhabi for the collaboration in many ways, including also in terms of helping us advertise and make seminars accessible to a large audience of scientists. It is my distinct honor to introduce today a distinguished figure in the world of science and public service, Dr. Stephen Chu. Dr. Chu is a Nobel laureate in physics, recognized for his groundbreaking work in Kuhnian trapping atoms with laser light. His illustrious career spans academia, research lab, and public service. In public service, he was the 12th United States Secretary of Energy, where he was very instrumental in, I think, fundamentally changing the Department of Energy, in particular introducing new elements in the Department of Energy, like the ARPA-E, the Advanced Research Projects Agency for Energy, which was set up to address energy challenges that industry couldn't meet, but that were very applied and needed a push to become commercializable. Previous to this, he was leading the Lawrence Berkeley National Laboratory as director, and he was instrumental in Berkeley Lab to get two large projects off the ground that are still very important Berkeley Lab. One is in terms of biofuels, and the other one is in terms of solar fuels. And they were both leading to large institutions, large research labs in Berkeley that are still existing today. And this was the time I worked for Steve, and I had the pleasure to have ongoing conversations with him about the high energy cost of supercomputers. And Steve had the right vision and said, this is going to be an issue for HPC, and it is an issue, but my colleagues haven't solved it yet. And then, of course, he was as an academic, and he has been a professor at Stanford. Now he's back at Stanford University, where he is professor of physics and molecular and cellular physiology. Dr. Chu's contributions have profoundly impacted our understanding of the physical world and advanced sustainable energy policies. Please join me in welcoming Dr. Stephen Chu, who will enlighten us with his insights and experiences about the challenges in getting to net zero. Welcome.
Thank you very much, Horst, for that nice introduction. It's a pleasure to be here today. Some of you may have heard parts of this, or maybe majority of it, but it's worth repeating. And it's a personal view of what some of the challenges are in terms of science and technology and how we can get to a more sustainable future. The sustainable future doesn't only include just energy, clean energy, but it also includes food, water, and the rest. Let me remind you of the average temperature of the Earth from 1850 to 2024. A danger point, the UN danger point was if we are going to go above 1.5 degrees centigrade. And for the first time, at the beginning of this year, we've just got above that. Where are we going to stop? Well, I'll just mention that, but that data point over here is a little bit 1.6 degrees centigrade. We have an understanding that this is due to greenhouse gas emissions from humans. This understanding is brought upon by the fact that the amount of carbon dioxide in the atmosphere can be calculated as be consistent with energy, typically burning of fossil fuel. The black line, the recorded temperatures. That tan thing is the uncertainty of many, many computer models. And if you take away the greenhouse gas emissions from humans, you get the blue line. Okay, so the major greenhouse gases, of course, carbon dioxide, methane. Methane is about 30% of all greenhouse gas emissions in terms of its contribution to global warming. But N2O, nitrous oxide, is also on the rise and will be playing a more significant role. We're beginning to see, especially over the last 5 years, 10 years, some changes. And one of the changes that we may anticipate is that as local agriculturals fail, that creates refugees, people who get desperate, they can no longer sustain living in their home country. And so they can migrate either within their country or overseas. This is one example where there's a projected water shortages. So we know that maybe 20 million international refugees has really changed the political scene of many countries, including Europe and the United States. And so just imagine 10 times more. It is a very destabilizing effect. So where are we today? This is where we are today. We're not making great progress. The current policies that will land us somewhere around 2.8, 3.2 degrees centigrade, we're above that, let alone the pledges and targets, let alone a 2-degree pathway. So I'm going to talk about what we need to stay below 2 or 3 degrees. And one of the things is that you need to go 2 or 3 degrees. You need to be close to zero net emissions by the end of the century. This, as I said, is already out of the picture. And the y-axis is net zero greenhouse gas emissions from every sector. And so that is a very significant thing. The other thing I want to remind you of is what we've done already to the atmosphere is not felt in the climate of the world. It's because the oceans are cold. If you go a few meters below sea level in temperate climates, you realize that it gets cold very fast. A kilometer or two deep, you're at 2 degrees centigrade. Very slow mixing between the surface temperature of the ocean, the surface temperature of the ocean, and the surface temperature of land determine the climate, and the very cold water. So imagine you've got an earth full of ice cubes, and as long as that cold water remains cold, you don't see the effects of global warming. How long will it take to warm up? Well, the mixing is about 50 years, maybe longer, maybe a little shorter. It could be of that order. So imagine sometime in the distant past, you heard that having a nice tan makes you better looking. And then 50 years later, that nice tan gives you skin cancer. Even if you stopped tanning yourself 30 years ago, your mutations have started. And that's also true of cigarette smoking. So this time delay is very dangerous as well. That's interesting. Why did it do that? Got lost in translation. It doesn't matter. This is one estimate of what the greenhouse gas emission is coming from. And you see that forestry goes from land use 0.2%. If you throw in food production and waste, maybe a quarter of all greenhouse gas emissions. And people are very aware of the rest of it, of transportation. You know, airplanes so far are a few percent of greenhouse gas emissions. And so this is very strange. Is this going to be true of my entire slides? Help here. There's no way I can plug in my computer. Because this is not a cable, this is a loss in translation. Another industrial revolution, the electronics semiconductor computer revolution. It was started by the invention of the transistor in Bell Labs in 1947, and another invention of the transistor a half a year later, based on some theories of William Shockley's, also at Bell Labs. But people don't realize the semiconductor revolution would not have occurred if it weren't for two significant inventions. And that is the zone refining method and the Tchaikovsky method of purifying germanium and then silver. When I was a young scientist at Bell Labs, my first year there was this old guy who would totter in. He's adjacent to my. After a while, we just talked about it. And I finally asked my department, who's that guy? I said, you don't know who he is? I said, no. He says, he's Bill Penn. He invented zone refining. He gets to do whatever he wants to do. And he said, oh, by the way, you remind me of these two young cavemen. They see this older caveman walking by. And one caveman says, who's that guy? And the other caveman says, oh, he invented the wheel. And the second caveman says, yeah, but what has he done recently? Anyway, so it was the fact that you can get semiconductors to impurities below a part per billion that means you can dope them at will. And it was that purity thing and doping that actually led the way. Optical communications. If it wasn't the fact that you can make silicon fibers very, very pure so that the absorption would be limited just by Rayleigh scattering of inhomogeneities, you couldn't have optical communications. So the Nobel Prize goes to Charles Kao, but it was actually Corning and then followed by Bell Labs that actually made fibers a reality. All right, so what about the solar revolution? If you look at the price of solar modules, starting way back when in 1978, it was a certain price, $100 per unit. It doesn't matter what the unit is. And now it's something like 30 or 20 cents. So the price of the modules has climbed by 99.6 since its invention. It continues to go down. This is what's happened in solar from 2010 to 2019. It's continuing to plunge. It will still go down further, and wind is also continuing to go down. These are great technologies, but you say, oh, if the price of solar energy, the so-called levelized cost, 25 years investment is cheaper than natural gas or coal or anything else, then the show's over. And that's not quite true because of various things. So anyway, here's what we need. In addition to inexpensive renewable energy, we need all the things, the backup generating capacity, energy storage, enhanced transmission distribution systems. And we have to figure out how to decarbonize the materials we use. All right, solar energy. A new kid is on the block. Whether it becomes commercialized or not remains to be seen. These are called perovskites, very complex materials, but huge progress in perovskites or in perovskites with silicon. And so these are the so-called rates of cell efficiency. In the past, perovskites would only last weeks, months. And now there's two groups that report accelerated lifetime testing of at least 15 years. And so you ask them why, and they say, well, look at the physics of what was going on. And so these grain boundaries were moving around. They would be recombination sites. We stabilized the grain boundaries, and it lasted longer. So I'm guessing that once these perovskites get to 25, 30-year efficiency, 25 is good enough. They may take over because you need a micron or less of the material to make it. It's low temperature materials. So there's no big energy investment. You can tailor the alloying of these materials to make multi-band gap semiconductors. So if these things do commercialize, instead of going down by a factor 2, it can go down by even more. Now, going down further than that, there's no incentive because it's such minor cost solar energy. But what do we actually need? Well, if you look at the solar resources around the world, they're very plentiful. The news, however, is anti-correlated with people because if you live in very hot, dry climates, there's no water, and traditionally that means people don't want to live there. And so you want to migrate this energy to where there are people, which means you need transmission and distribution systems. So this is a snapshot of the solar resources in Europe. Northern Europe especially doesn't have very good solar resources. And so right now Europe is beginning to plan high voltage DC transmission lines, taking from abundant renewable energy countries like Iceland and Norway and bringing them to England and the rest of the continent. There is talk, this is not planned, of tapping into the solar resources of Northern Africa, the Middle East, and then bringing them into Europe where the markets are. The transmission of high power electricity, high energy electricity is an issue. These are photographs of 12 gigawatt transmission lines in China. Those are controlled on the wires. So these are very big. So that large standoff is because this operates at 1.1 million volts. And it's known that if you increase the voltage, the amount of resistive losses scales inversely is V squared over R. You go to higher voltage, double the voltage, you have a quarter the transmission loss. This is what a transformer looks like. Again, those are people. And so another thing, and this is very interesting, is that the wires that carry this tremendous amount of power are not copper, they're aluminum. Aluminum's a lot lighter. The current wires have a steel core. Steel is not a good conductor, but it serves as, it gives you tensile strength. So you can string the wires between the towers. Under development and beginning deployed is a carbon center with a space filling aluminum that's now annealed, so it has higher conductivity. So this is in the offing, but there's something significant about this, and that is looking at the materials. So let's step back and look at the materials we use, the materials we find in the earth. And on this y-axis is in logarithmic scale, the abundance in terms of tons of material. And you see some of the things just jump out at you. Concrete is number one, followed by oil, coal, natural gas. Of the stuff we use in the earth, that's the most of the stuff we use, are energy and concrete. Next column. Then you have to go another order of magnitude or more before you get to the other metals. And you see the copper's down there at 10 to 7 compared to 10 to 10 in terms of oil and coal. So 3 orders of magnitude less. And there is an anticipation that not in the next decade, but probably in the next half century, copper becomes a problem. Because as you electrify, you need more and more copper. And so that is an issue. If you look at the steel that we have, it's poor conductor, this is conductivity. And here you have copper, silver, gold, all these other things over here. There's aluminum, not as good as copper, but a lot lighter weight. And then you have over here carbon fiber, which is better conductivity than steel, much better tensile strength. So here's the challenge. If we are going to start to run out of copper, and the price of copper, those who follow the financial markets, is zooming through the roof right now, but that could be temporary, then capitalism will respond and you get more copper mines. But fast forward 50 years, doesn't matter. As you electrify, you're going to use more copper. What if you can take carbon out of the ground and turn it into a good conductor? There's so much carbon in the ground, you will never run out of carbon or copper. Okay, now, if you can get carbon in the form of nanotubes, then your orders of magnitude better than any metal. But again, it has to be commercial, so it has to be as inexpensive as copper. So one challenge is figure out how to make copper particles, ideally in the form of self-assembled nanotubes, cheaper, and then this is gone in terms of the natural resources we have access to. Wide bandgap semiconductors. Why is this important? Because what's a wide bandgap semiconductor? The first semiconductor transistors were germanium. And it was known even in those days, in 1948, 49, that you want to go to silicon, which just has higher band gap, less noise, less thermal noise, better stuff, better transistors, silicon. But there's other materials, gallium nitride, silicon carbide, and finally diamond. Diamond is perfect, except for one thing. It's got a huge band gap. The biggest, it has great thermal conductivity, so you can dissipate lots of energy. And the only thing is it takes on boron, but we haven't figured out a counterpart to the doping of a diamond. In the meantime, silicon carbide is becoming the power transistor material of choice. When I was Secretary of Energy, we actually invested in how to make better silicon carbide and gallium nitride, because we said the people who manufacture equipment are going to do research in materials. And so aside from a place like Bell Labs, which doesn't exist the way it used to, who's going to make an investment in this? So we started doing this in the government. And so right now, silicon carbide is the high voltage semiconductor of choice. If you pay attention to electric vehicles, you will notice that the voltage that operates the electric vehicle motors are going up and up and up. They're doubling, and they're going to double again. Mercedes has announced they're going to go to 800 volt systems. Why? V squared over R, less copper, lighter weight. Okay, and it's only because power electronics became less expensive. And so the better power electronics gets, the higher the voltage you get. You're going to get electrocuted whether you're at 1 kilovolt or 0.2 of a kilovolt. If you can get electrocuted at 12 volts if you lick your fingers to touch the battery, by the way, just be warned. Okay, so this is something else that is in the future. Horst explained about the energy of compute. This was the energy, this graph was made in 2015, where this divides the electricity energy between the networks, the production of the communications technologies, the consumer devices like televisions, computers, that's the thing in yellow. These, your widescreen TV that's about this big is 200 to 300 watts. Okay. There's a technology possibility there of lowering that by an order of magnitude and still getting the same brightness. But the real killer is going to be data centers, the stuff in green, because of the demand for artificial intelligence, which has an insatiable appetite for compute power. So going up by a couple of orders of magnitude in compute power for machine learning is the demand will always be there. They'll take 2, they'll take 3, they'll take 4 orders of magnitude. The other application of compute power is Bitcoin mining, which is very sad, should be outlawed, because the only real use of Bitcoin mining that I could see is money laundering. But machine learning and artificial intelligence does have some societal uses. So what do you need and what do you do about that? And so there again, you can squeeze on CMOS technology and you can get factors of 2, maybe 3 by getting smaller CMOS, lower voltage CMOS technology, which is the stuff that rules the world in electronics today. But there are other possibilities. One is a material called ferroelectrics, made from perovskites. So what's a ferroelectric? Well, think back to those of you who are old enough to remember, there used to be things called magnetic core memory. You send a little current through, you magnetize a little circle of magnetic material, and it stays magnetized. So you can turn on the current to magnetize it, and then you no longer need any current. So you can switch it to 1 and 0, depending on what you do. In semiconductors, if you look at, say, DRAM, it's a charge on a capacitor, but the capacitor leaks, so you need a transistor to constantly charge the capacitor. So that memory is always on. And when you do compute, you similarly need capacitance, so you're going to need these flows. Turns out with ferroelectrics, you can pass a small amount of current through, you can flip the spin of the material, and then it stays flipped. And the first application will be like magnetic core memory. It will just be a flip of spins. The second application is, it turns out you may be able to do logic with ferroelectrics. And so a person that I recruited to head my solar program when I was head of Department of Energy, Ramesh, is a co-founder of a company called Kepler Compute, which is trying to make ferroelectrics a reality. And things are coming along, whether this company does it or not, or whether some other company does it with ferroelectrics, I don't know. In fact, you should never count out silicon in both solar generation and compute, but this is an opportunity where you can go down to maybe 100 millivolts of operating power and very little energy. So that's a possibility. Now, energy storage. This is the picture of my favorite battery. Let me tell you how it works. When the wind blows, the sun shines, you pump water. That's the energy intensive thing out of the ground into a holding pond or water tower. And then when you need the water, you open up the valve. So pump storage, plus lifting water up in a gravitational gradient, is 95% of all energy storage today. This is an example of pump energy storage in different countries. China, led by China, the United States, Japan. The United States has woken up to the possibility of enhancing our pump storage. Enhancing pump storage means you have an existing dam, you have a turbine, and the turbine can be made to go backwards, so it pumps water up the hill, and then you can let water back down. Doesn't sound very efficient, but if you've got 30, 40 meters or more, you can be 75% round trip efficient. So it is as efficient as a flow battery. So the United States is planning to add another 1.9, at least in permits. Whether they go through this, don't really know. So what is China doing? Well, China is trying to add another 34 gigawatts of pump storage. So they are planning to have more pump storage than the rest of the world combined. Why? Because if you have an existing dam, it remains the cheapest form of energy storage for the next 20 or 30 years. Beyond that, I don't know, because you could have technological breakthrough. All right, so anyway, but not everywhere has mountains. Most don't. So we are looking also to commercial batteries. That circle is what the Tesla battery is today. And I'm predicting within a decade or so, it will go up to here, perhaps doubling in energy density per unit weight and going up in energy density per unit volume of 35%. This is not an idle prediction. Why? Because I'm on the board of directors. Well, I do battery research in my own research, but I'm also on the board of directors of a battery company, and we're sending out samples that are double. Now, does this get into EVs? Not for 5 or 10 years. It'll take at least 5 or 6 years to go through safety testing. In the meantime, the cost of batteries is going down. So this is the cost of batteries on the y-axis, and it's going powers of 10 from 200 to 2,000, 1,000. And this is the amount of batteries in terms of megawatt hours that have been produced and shipped. And so once the technology begins to develop, it turns out that it begins to follow what's called the learning curve. As you increase the amount of deployment or production by a factor of 10, then the cost goes down by some fraction. There's no law of physics or finance that determines what the slope of the learning curve is, but it just happens that it's true in just about any technology. And so the learning curve is fantastic. By comparing 2020 to 2030, and starting in 2000, the prices dropped by a factor of 20 so far, and another factor of 2 or 3 is inevitable because the OEMs, the car manufacturers, are saying they only want to pay $100 a kilowatt hour for any battery they buy from whatever battery manufacturer. So that's good. So when do learning curves stop? Moore's law is an example of a learning curve, and it stops when the dimensions become atomic dimensions. The design rule for today's semiconductors is 2 nanometers. And when it gets to it's not going to get to 0.2 of a nanometer. That's one atom. But it's getting close. And so they're doing other things to effectively continue in Moore's law, but not just on the scale of the feature size. But another thing that could stop a learning curve is you run out of the essential materials. And so, again, let's step back and look at where the materials are and how abundant they are. And the most abundant solid material on Earth is silver. That's sand. Okay. And you look up there, aluminum is pretty good, sodium is pretty good. And you go down and you look at that red line, that's where lithium is. Lithium is about as abundant as nitrogen and chlorine. It's not a super rare element. It's really how do you get lithium out in high enough purity. And if you could get lithium out of seawater, now lithium in seawater is very dilute. It's 1 lithium atom per 20,000 sodium atoms. And there's lots of other ions around in addition to sodium. And so is it possible to extract lithium from seawater? And so when Chung Lu was a postdoc at my group and also a graduate student in East Way, she's now an assistant professor at the University of Chicago, she began to develop methods of taking lithium in aqueous solution, water solution, putting them into a cheap battery material. This is iron phosphate. And so the lithium atoms were intercalated between these planes of iron phosphate. And you can arrange it so the lithium ions would go into the battery material and would exclude sodium atoms to a high degree. And her latest results that she did when she was at the University of Chicago, she can start with seawater at 20,000 to 1 ratio, and she can get 8 times as much lithium as sodium on 1 round trip. So that's perfect, except for one thing. It's a battery material. It depends, you have to diffuse lithium into the material out, which means it's essentially a 2-dimensional system. Battery is only 100 microns thick. You want to do this at scale, you've got to scale it in a way. So we don't know if this is going to work. In my group, we're developing different ways, not depending on this method, but I'm convinced that you can get lithium out of seawater, just lithium, and throw the rest back. Right now, we get lithium by taking lithium mostly underground aquifers, very salty water. You pump it up, you let it evaporate a couple of years. It gets this really icky stuff. In the process of pumping it up, you've taken underground water with all its contaminants and you've polluted the ground. In addition to that, because you're pumping so much salt water out of the saltwater aquifer, freshwater aquifers, which are near the surface, then sink down and become salty water. So you're depleting the fresh water as well. So this is not a good way to extract lithium. You want to get lithium out of salt water and just pump the salt water back in the ground, leave all the other pollutants below. It's something that I think is eminently possible, which is why I'm continuing to work on this. Another thing is batteries, conventional batteries. The highest energy density batteries where you have an old metal atom. And if it's a lithium ion, it would be a lithium metal ion, but it doesn't have to be lithium. One is not wedded to lithium. And in fact, with utility scale batteries, you can't use lithium. But the trouble with a metal battery, any kind of metal, doesn't have to be lithium, is that when you charge very quickly, there could be surface imperfections. And this is an example of a sulfur lithium metal battery. Why this? Because it potentially has the highest energy density of any lithium technology we know about. But if there's a little bump on the surface of the lithium, that is a higher electric field. It induces the lithium to deposit there, and that bump grows into dendrites and it shorts. And so if you can prevent a way of doing this, of getting rid of these dendrites, you're home free. There's a bunch of ways people are thinking of doing that. We also are thinking of ways of doing this. And this is example, my graduate students and postdocs don't want me to talk about until we submit a paper. But in any case, this is a lithium sulfur battery. And if those of you know anything about lithium metal batteries, they begin to decline, and after tens of cycles or hundred cycles, it's just flat. So this is the coin cell that just was absolutely flat after 300 cycles, and it failed because the lithium, the known electrolyte we were using, and the sulfur undergoes a chemical reaction. If we just try the half battery of just lithium going in and out over 1,000 cycles, no change. So we know that this prevents dendrites from forming. Similar is true of aqueous batteries. You want aqueous batteries for utility scale because they don't catch fire. And there's a problem with aqueous batteries. You can have any ions you want, sodium, potassium, zinc, manganese. It's not going to be lithium, but you have to, if you have it in water solution, aqueous solution, you can begin to split water and make hydrogen or oxygen. So that means the battery has to work below 1.3 volts, which means instead of at 3.5 to 4 volts, you're much lower in energy density. Again, after we submit, we have to do this research, but hopefully we'll submit that in a couple of months. We think we can maybe get around aqueous batteries being below 1.3 volts. So these are some of the challenges. If you guys can think of ways of doing this, there will be a very big market. Okay, so we have pump storage that works very well. Hopefully in the future, it can still do 95% of energy storage. But again, not everybody has mountains and water sources. And so you will need a turn-on source, either natural gas with carbon capture or nuclear power. There are issues with nuclear power. The major issue is we forgot how to build them on budget, on time. And so a 1 gigawatt reactor, which used to be about $1 billion, now they're coming in at $2 to $5 billion, and maybe even worse. So that cost overrun actually literally forces utility companies to go bankrupt. And so we need to bring this back to, $1 billion. There are a new possibility of what are called small modular reactors. That's an example of one by a company called NuScale. And so these nuclear reactors can be built hundreds or thousands at a time. That's the promise. And so you get economy of scale by economy of numbers, and they can be built in a factory with very good manufacturing tolerance and shipped around the world. That was the dream. NuScale just had a contract, their first contract lost because they went 50% over budget. And so this still remains, how do you build even small modular reactors on scale and budget? That has a higher probability, but you need someone to underwrite the first 100 in order to get the economy of scale. When I was secretary, we funded a Westinghouse, B&W, and NuScale for engineering drawings. That's 2010, 11, 12. But they needed more help than that. But they mostly need patient capital. If these things work, that would be very important because they can be designed to be virtually contamination proof. They have enough heat capacity that they will never melt down. And so if you can imagine putting these in islands where you normally won't think of having a nuclear reactor because of contamination issues. You can also think of them, companies are beginning to think of them, an oil refinery or this, that, as behind the fence within their own thing. Having couple hundred megawatts is a good deal. Data centers would love these because that's the same scale. A couple hundred megawatts is a typical data center. Okay, there are other forms of energy storage. Prominent among them is hydrogen, and so there are different colors of hydrogen. The hydrogen commercially used today is made from steam reforming methane gas, natural gas, mostly in the form of methane. And this is $1.50 a kilogram of sort of U.S. prices of natural gas. There's blue hydrogen. That means you take the carbon dioxide you create when you turn natural gas into hydrogen and you sequester that. It's maybe double in price. And there's green hydrogen, which means you use some non-carbon emitting form of energy, nuclear, wind, solar, and right now it's very expensive because electricity is very expensive. Now, having said that, you do want eventually to get to green hydrogen because poking holes in the ground to extract natural gas means between 2 and 5 or 6% of the methane leaks out. It's not recovered. And methane, again, is 30% of the global warming. But hydrogen could be used to decarbonize steel. It's a reducing agent. It's used now in plastics, chemicals, fertilizer, aviation fuel. Those are its possibilities. Hydrogen is very leaky. And that's a problem because after we determined how to detect natural gas leaking remotely, we found out that there's 2 or 3 times more natural gas leaks from the ground than we thought previously. So what about hydrogen? Well, it's very hard to detect hydrogen gas. It doesn't have a strong chemical signature at all. It's a symmetric dipole. And so when you think of actually having hydrogen pipelines until you can determine whether they're leaking or not, our experience with natural gas is you need natural gas detector to find out if the pipelines are leaking. So there is a technological way out. You don't have to detect the natural gas hydrogen itself. You can detect something where hydrogen undergoes a chemical reaction. That could be made pretty compact. You can get a hydrogen detector that's literally this big. Okay, so it's a chemical reaction. Well, when it's this big, you can put it on a drone. And if you can put it on a drone, you can have the drone buzz around. And so there are technical solutions to this leakage problem. It's not out there yet, but it's anyway. It's so I think hydrogen will be part of the solution for sure. If you want to use electricity to make hydrogen, right now we use expensive rare earth metals. That's an impossibility. But there's another alternative which is coming along nicely. Again, another friend of mine who I hired as Secretary of Energy, Robbie Prosper, is now the Chief Technology Officer of a company called Bloom Energy. And he wrote me an email a couple of months ago and said, we just got a little bit of a breakthrough. Our electrolyzers, you put in electricity, you make hydrogen and oxygen. Remember, fuel cell it can go in the reverse. You can take hydrogen, you make electricity for electricity generation. But imagine sending electricity over transmission lines and producing the hydrogen on the site where you need it. Then the transportation pipeline problem goes away. 88.5% thermal efficiency is spectacular. The PEM electrolyzers are 60% efficient. But before there was a lifetime issue, that's being solved. And so they've operated at slightly elevated temperatures, but at economy scale, temperature is not an issue. Think of petroleum refining. So this is a very real possibility that you send hydrogen by electricity over wires and you produce it at the site. In the end, if you're in a place that has a lot of renewable resources, a lot of wind and solar, wouldn't it be wonderful if you could take energy, in clean energy ideally, and you can turn carbon dioxide and water into hydrogen and CO, but that's the beginning of stepping up to make a linear hydrocarbon chain. This linear hydrocarbon chain is useful. This is gasoline, diesel, jet fuel, because it is one of the highest forms of chemical energy we know about. That's why we use it works so well. And so is it possible to put hydrogen in form of a carrier, put it on a tanker and ship it? Why do you want to put things on tankers? Because there are no electrical lines across the Atlantic and the Pacific. But if you put crude oil on a tanker and ask the question, how much does it cost to transport this crude oil from the Middle East to, let's say, Japan or China? The answer is, it turns out to be about 2 cents a gallon of gasoline. Okay, so intercontinental transport on a slow tanker is really cheap. And so if you can turn hydrogen into a liquid that you could ship at room temperature, then it becomes this cost. If the conversion costs are very inexpensive. A lot of work on this. So far, nothing commercial. There are liquid organic hydrogen carriers that cross across my desk weekly or certainly monthly. Ammonia is an old technology that seems to be the leader at the moment. You can liquefy ammonia at high pressure to lower temperatures, but not like liquefying hydrogen, which is too cold. So again, another challenge, turn hydrogen to methanol cheaply, and that you've got, it's great because methanol has other sources, uses as well. But that again is, so far, no one's figured out a way of doing that inexpensively. But think of super tankers as intercontinental transmission lines. All right. So again, I just mentioned this. I talked about nuclear before. The biggest thing to nuclear is the budget of construction costs, things like that. There are some people concerned about nuclear safety. And so what I try to remind them is on an overall scale of energy sources, if you look at the number of deaths per unit of energy generated, it's leads the way by brown coal and black coal. Those are 32 and 25 deaths per terawatt hour, followed by oil, biomass, that's like burning wood chips, and so on. So where is nuclear? Nuclear is down here. It's a little safer than wind. Why is wind dangerous? Because people can fall off wind towers. It's like solar, people can fall off roofs. And so nuclear, including Chernobyl and Fukushima, is in between wind and solar. And the two orders of magnitude safer than burning wood pellets because of particulate matter when you burn wood pellets. So safety should not be an issue. I emphasize it should not be an issue, but it is. But anyway, now sequestration is another issue, spent fuel. And the thing about spent fuel is you've got to dispose of it for a very long period of time, tens of thousands of years, up to hundreds of thousands of years. New technology developing and just drilling holes this big in diameter, oil boreholes. And if you put nuclear waste down a couple of kilometers, you can access very stable geological formations there where leaking is not an issue. So again, they do have some technological solutions. Let's talk about fusion. There's magnetic fusion. This is a picture of ITER a couple years ago while it's being constructed. This is a cartoon picture of laser fusion demonstrated a little more 2 years ago. And in that instance, you have many laser beams impacting a gold cylinder that creates X-rays that then implode this little bubble of, it's a diamond bubble, a very thin shell diamond, which you've evaporated tritium and deuterium, and it's got to be really smooth. It's got to be atomically smooth. So when you evaporate tritium and deuterium, it's polycrystalline, so you have to anneal it maybe half a dozen times. And so that takes a day to make one of these. And then it's suspended by atomically thin plastic films, 50 angstroms in thickness, in this hollow around this gold cylinder. And then you hand carry it very gently to where you're going to put it in front of this laser, and you lose half the targets because the thing breaks this 50 angstrom thing. And so if this is going to become commercial, you have to shoot them in 20 times a step into something with a lot of gas and a lot of turbulence because the previous nuclear explosion. And so it has some technical challenges. Similarly, magnetic fusion, also cold fusion has technical challenges in terms of neutron damage. The neutrons displace the atoms, so they move around. In a fusion reactor, anticipated maybe 100 times in 1 year. They're moving around, and then neutron activation makes helium, alpha particles. Then if it's moved around, instead of polycrystalline metal, it becomes little metal, Swiss cheese, and so material falls apart. We do not have a solution yet for the neutron damage after all this time. And unless we solve that problem, this is not going to go forward. You can make a scientific experiment, but to make it run year in, year out is not a problem. Right now, the engineering projections are you have to have a sacrificial layer of stuff to prevent the vacuum chamber from being destroyed, but that has to be changed every 5 years, and it's radioactive. So it's not a 1 week exchange material. And so the estimate of deployment of commercial fusion is it's not going to be in my lifetime. It's going to be greater than 40 years. Also, inertial fusion. Friends with the guy who made inertial fusion work, and he agrees with me. It's at least 40 years, maybe never. So does that mean we should not invest in fusion research? Absolutely not. Because if it does work, it'll be great. But it's a long bet. And just realize it's a long-term bet. Okay, so anyway, all right, agriculture. We need a fourth agricultural revolution. And remember, it's 20 to 25% of all greenhouse gases. Let me remind you of how agriculture started. This is a map of the proxy of the temperature from glacial isotope samples. It's using oxygen as the proxy for temperature, and present time is on the right-hand side and is going backwards 400,000 years. And we're in a relatively warm period. There are ice ages, another warm period, ice ages. So humans were roaming around the Earth for 250,000 years. Roughly, the human brain is, been around for a while. And yet agriculture only started 12,000 years ago. But it didn't just start in the Middle East. It started in 4 or 5 places around the world within a couple hundred years. Okay, so, and then what happened and why did it take so long? Let's blow up that more recent history. The climate stabilized. As soon as, instead of going up and down like crazy, it stabilized, people say, I can raise crops. And then once you raise crops, you don't have to be hunter-gathering, going from here to there, and you can grow food, and you can create wealth, and you can get kings and physicists, and all the other things that are as productive as the farmers. But anyway, it was the stabilization of the climate that happened. That was the first agricultural revolution. Was the domestication of wheat, rice, cattle, chickens, developed yeast for bread, first irrigation, fermentation of grains and fruit for beer and wine. That was the first one around this time. Second agricultural revolution began right here. This is a graph actually made by an economist who got the Nobel medal, sometimes called the Nobel Prize in Economics, Robert Vogel, and he said, the second agricultural revolution preceded the industrial revolution because it created another flood of wealth that could allow that to happen. And what was the second agricultural revolution? It wasn't technology. It was the fact that it allowed people to put a fence around their land and said, you guys can't use it and graze your cattle or whatever. I'm allowed to use it for my purposes. And suddenly it became profitable. So the profit motive and better trade was the second agricultural revolution. What's the third agricultural revolution? Well, it came in 2 parts. First, the ability to make fertilizer, nitrogen-based fertilizer, began with nitrogen, the so-called Haber-Bosch process, which got Fritz Haber Nobel Prize in 2018. It's called the Haber-Bosch process. So Fritz Haber said, well, this is bad. So they gave it to Karl Bosch in 1931 for the Haber-Bosch process. So they had to invent a reason because they already gave a Nobel Prize. They say, well, for the invention and development of high temperature, high pressure catalysis, which was the Haber-Bosch process. Okay, so 2 Nobel Prizes, and then in 2008, Erdl got a Nobel Prize for surface science, and they said in the Nobel Prize, they said, we're beginning to actually understand how the Haber-Bosch process works. 2.5 Nobel Prizes because it fed the world. Another great advance was the crossbreeding of plants, led by Norman Borlaug for wheat, dwarf strains of wheat. So on the left-hand side, that's Norman Borlaug pulling his dwarf strains. The right-hand side, standard wheat. Very, very productive. The production of artificial fertilizers and crossbreeding of plants meant by from 1961, where there's 3 billion people, to 2021, where there's 7.9 billion people. This is the amount of land put under cereal production. It increased. The productivity increased. And so, in fact, the productivity increased 300%. So this is really fantastic. Now, having said that, there are greenhouse gas emissions. There's lots of greenhouse gas emissions from some of the animals we eat, because beef, for example, they have a lot of microbes in their stomachs that steal food away from the cattle and turn it to their own, and then the cattle bursts out methane. And so beef leads the list in terms of greenhouse gas emission, followed by this. So now, the possibility of outlawing beef consumption, especially in the United States, is like impossible. But younger people are eating less beef. Some older people may be eating less beef or no beef. But then pigs and chicken are much better than in greenhouse gas emissions. But having said that, vegetables, rice, soybean, tofu, those things are much better than that. So if you look at the greenhouse gas emissions of the world, in terms of countries, there's China leading the way, followed by the United States, all the EU plus Great Britain. India is about to take off. But if beef and dairy cows were a country, they would be ahead of the United States and EU in terms of greenhouse gas. Aside from encouraging people to eat less beef, there's also scientific solutions, maybe. These are parasites. They're stealing food away from the cattle. Can you inoculate the beef or change their microbiota so that they don't make as much methane? And the answer is yes. And so we know that if you feed a type of seaweed to the cattle, they birth 9% less. The only trouble is they don't like the taste of the seaweed. So there are other possible solutions? The answer is yes. I mentioned that you can look at a soybean plant or other legumes. And on the roots, in the border between the roots and the soil, there are some microbes that take nutrients out of the soil and turn into plant food, and they feed the plant. And so, having been inspired by that, a company in the Bay Area called Vivid Bio said, can we make microbes that, when planted with corn, will enter into the same symbiotic relationship? Corn is very fertilizer intensive, and so can you do this with corn? And the answer is you can, but it only works at half the fertilizer, not all of it. And it doesn't work in all soils. And so that's all good. I used to be on the board of a company called Zymergen, used to be maybe, well, I'll tell you about it in a second. So Zymergen uses synthetic biology to alter the genome of these microbes so that they can feed plants. And it worked. The only trouble with this is it took about 8 years to develop these microbes. 8 years is too long. And the reason it took 8 years is because at the time, Zymergen can only alter one gene at a time. and the solution required 12 genes and you needed to optimize, you take many, many iterations very slowly. And so that was the bottleneck. The company eventually went belly up, bought up by another biotech, synthetic biology company, which business plan is we're not going to develop anything. We'll be a foundry. And if someone develops something, we'll have the machines to grow up the bugs. But the promise of synthetic biology has not come through because of that long iteration time. But because of that, I said, well, if you could put in 10 or 12 genes at once, because you can type out the genes on a typewriter and put them into DNA. That's not the issue. You couldn't get the genes into bacteria, but you can't get it, because usually it's viruses that are used that are limited to 10 kilobases, which you need about 6 as a minimum to get in a reasonable size gene. So we're developing methods of getting in 50, 100 kilobases at a time. So you can do it and massively parallel. So many, many cells all at once, not just, one pipette calculation. And so if you can do that, then synthetic biology could take off, because we know from other things of these randomized mutations of the Francis Arnold got a Nobel Prize for, Professor of Chemical Engineering at Caltech. So you can make many, many experiments all at once and several iterations, and you can do some real programming. But those were random mutations, and for synthetic biology, you have to put in mutations you want to put in. So you can't use Francis Arnold's trick. Okay. All right. Now I said we're likely going to be over 550 parts per million. Right now, the cost of carbon capture is way too expensive. In my opinion, got to be below $50 a ton, and maybe $100 a ton for direct air capture. It's much more expensive than that. Also, let me tell you about the scale. We're now emitting 52 billion tons per year of carbon dioxide equivalent, over 40 billion tons per year of carbon dioxide. Because of airplane fuel, agriculture, and other things, cement, steel, plastics, everything else that needs to be carbonized, it will take decades, maybe a half a century, maybe even longer. So we'll need to capture carbon dioxide, and maybe of the scale 10 or 20 gigatons of the 50. Okay, how much is 10 or 20 gigatons? Well, it's a lot. If you think of pumping it underground at high pressure, the carbon dioxide becomes a superfluid, the density becomes close to that of water, maybe 0.7 of water. Look at all the land mass from garbage landfills. It's 2 billion tons of solid landfill a year, the whole world. But now we're talking about 20 billion tons of something 4 times lower density. Okay, 80 times the volume of landfill every year. This is significant. Okay, it's a big deal. So think of all the oil and gas we took out of the ground. Remember that earlier thing about that's most of the stuff we're taking out of the ground besides cement? We're going to have to start putting it in the ground at the same massive scale. By the way, the oil and gas industry has the best technology to know how to do this. So we need your help. In the end, we fixed in the crops we plant, we're fixing 10 to 18 gigatons per year from photosynthesis through this solar powered carbon sequestration in the form of biomass. If you use what you use for food, for fibers, for other things, you let the rest rot and it gets recycled with carbon dioxide and methane. But suppose you start using that crop residuals in terms and figure out how to sequester it safely so it doesn't turn into carbon dioxide or methane. This is of the scale you need. You still have the volume problem. The density is maybe twice as large as superfluid CO2, but not much better. But anyway, this is a very real possibility. Okay, so now let me conclude. about energy transitions. From the start of the Industrial Revolution, where we began to use coal, you see coal rise peaks, and then we began to use oil and natural gas. And then later on, we began to use hydro plus nuclear plus wind and solar, just a sliver near the top. That's one way of looking at it. Okay, so from this way of looking at it, you say, it takes 60 years to make an energy transition. But let's look at it a different way. What is really happening, not on a fractional basis, but what's really happening, coal, oil and gas, and all the other stuff. This didn't go down. We just added. Okay, because India and China and many other places still use a lot of coal, will continue to use it until it gets so much more expensive than anything else. And so from this, we're not transitioning to a clean energy solution. You have to be reminded of history because the economics really have to be very compelling. So at this moment, what I see is we still are heading to over 3 degrees. We're on a ship that takes at least 60 years to turn, maybe 100 years. And we're still heading towards an ice. I'll stop there.
Thank you very much, Professor Chu. We have time for questions from the audience.
Yeah, Steve, thank you very much for the presentation. A question for you, have you thought about possible usage of geoengineering, seeding this and that in the atmosphere, trying to, rather than reduce the CO2, but just to make it different? Yeah, directly.
Yeah, so the question is, what about geoengineering? Because implicitly, it's going to take a lot of time to get these technologies economically viable and properly deployed. And the answer is, when our secretary says, maybe in an act of desperation, we can use seeding of particulates fine, not sulfur dioxide, because that makes acid rain and destroys the ozone, but other cheap particulate matter. If spread in the stratosphere with airplanes, it can stay up in the airplanes for about 1.5 years and then comes down. And so that would work. It would be much less expensive. And the trouble is, and the good thing is, if there are unintended consequences, you can stop it because it all comes out after 1.5 years. But so geoengineering is in the cards, but let me also remind you that agriculture is the biggest form of geoengineering. Half the arable land in the world is under agricultural production or forestry management. And so that is ready geoengineering. So we've been there, and it has good and bad consequences. So, but geoengineering will probably be a needed part of the solution.
Quick question, and thank you very much for the presentation. Just a quick question. Could you kind of comment on what are your thoughts on space mining? Space mining, yes, or resources.
The space, you mean like solar space?
Yes. Space.
Oh, space mining.
Yeah.
Oh, it's pretty expensive. Probably before we do that, these are for some of the more non-so earth abundant materials like cobalt, nickel, things like that. People also think of mining the seabed floor with this. I don't think mining of asteroids is economically viable. It just costs too much to get something out now, and then you don't, you can drag these asteroids back down and land safely. Landing safely is an issue. So, but I don't know. I mean, but now I thought you were going to ask me about space solar, which I used to think was insane, but no longer think it's insane, especially if you can put thin film solar that and our experience with the so-called sails of very low mass stuff. Not completely crazy, but I think one has to keep an open mind about everything. The most important thing is how as we use these non-replenishable resources, whether it's copper or lithium or you name it, we have to change that, to use them more sparingly and make them totally recyclable. And that has to be designed at the get-go. Tesla batteries are not recyclable. The whole thing's embedded in pocket. So it wasn't designed to be recyclable. So these metals, copper is recyclable. We know this in the United States because people steal copper out of buildings. When there was a blackout, I just sad story. Tropical storm Sandy hit the New York metropolitan area. I go there as Secretary of Energy, tour around and look at a substation. And the people in the substation say, you can't believe this, but during this hurricane or tropical storm, they invaded the substation and they took out the copper. They could have killed themselves because they could have been electrocuted, but the power was there. But it was like crazy. So the resource we've been using have to have a total mindset. Again, I'll leave you the thought. So much carbon in the ground could be a good conductor. You make $1 zillion. That's the way to do it.
That's a question.
Hi, I'm Shaw, professor of physics here. If you were given full powers, what would be the first thing you would do to steer the boat?
If I was given full power,
Yeah, like the board, whatever, United Nations, what would be the first thing you would do to steer the boat, to avoid the collision?
Yeah, that's a very good question. I used to think of that because being Secretary of Energy, President of the United States, not enough power. I would align the incentives. You don't want to, dictators don't really work. I'm a full believer in aligning incentives so people can make money doing the right thing. And so you start with building energy efficiency into the system and rewarding people who build buildings as it starts to take advantage of all the technologies we have. We're just throwing away energy. And so that would be the first thing I do. In terms of some of these other things, if we have technology that exists, like transmission lines, in the United States, it takes 11 years to get permitting to build a transmission line, 9 years of court battles, 2 years to build it, maybe 1 year to build it. And so that's crazy. Okay. Other countries have figured out how to get permitting done faster and still being sensitive to environmental concerns. So faster permitting would be another thing I would do. Then the research areas, I would say, I think there's some of these areas that are getting ripe for commercial investment. Again, I stress the commercial side rather than the planned economy side, because the experience in the past has told us that actually the profit motive is actually much better than a state-run government in getting things to work. That's just a history statement. So I would do things like that. So being a supreme dictator means you want to stimulate people to use ingenuity and profit motive to do the right thing. Thank you.
Questions? Yeah.
I'm understanding from the government the energy transition. You touched upon the point on efficiency. The other area which I think if coming to the human behavior, for example, how big can make when the human start to changing preferences and maybe, for example, eating less meat, for example, using community modes of transportation,
right,
and switching off the lights at the right time or not using it. So how big an impact can the human behavior make on the transition?
It could make a huge impact, but then it's age dependent. What I witnessed, I'm a teacher at Stanford, and among the younger people, there's a lot of vegetarians or people who eat much less meat. The people who are 70 or 80 years old, forget about it. Most of the people that age said, no, I'm going to do exactly what I'm doing. in the United States, owning a car was the American, owning a house and a car was the American dream. A house in suburbia with a yard in it. Beginning to change among the younger people. Getting rid of the number of cars per family used to be about 1 or 2 per family. Now at least 1 per person. And so what's going to replace it? Well, if public transportation exists and it's good, then it does work. And we have a few existence proofs. The Paris subway, the London metro, Washington DC is limited, but its metro is pretty good, and New York subway system. But it has to have lots of stops, and it has to be heavily subsidized because it has to be inexpensive. And for whatever reason, I can't figure it out. Public transportation cannot be a standalone entity. I haven't figured this out, but maybe you financial people have figured this out. So there are things like that that can be done. The danger that I was talking about is too far in the future. And even though the weather has been getting pretty weird in the last 5 years, that's the inverse tip of the so-called iceberg, right? I remember the damage we've already done. It's not visible for another 50 years. Okay, so the impact, if all the work it's going to happen 50 years from now is visible today, it could motivate many more people. Yeah. But there are large financial losses, personal losses, even deaths. But the way it is now, it's too far in the future, and it's not visible enough. And so that is a problem. How do you get people excited about something that's invisible now and not going to affect their lives is something we should try to understand, because for the first time in the history of human beings, science said what you're doing now is going to affect the world in a very adverse way 100 years from today. Science has never said that before. So what's the reaction? Don't believe the science. That's not, that, as Al Gore used to say, that's an inconvenient truth. Now, unlike Al Gore, I believe in carbon capture. It is a necessity.
Other questions?
Just. The largest carbon intake is the ocean. Is there any safe geoengineering techniques which will increase the carbon intake by the ocean?
Okay, so the oceans take up a lot of carbon dioxide. Carbon dioxide enters the ocean as CO2. It gets converted into bicarbonates and then at high enough concentration carbonates. So it is a tremendous sink of carbon dioxide. It's most of the carbon dioxide. The ocean and the land, even though the land, all the trees, the ocean is half of it. Water absorption of carbon dioxide is the means of capturing carbon dioxide. But right now, the technology that people are now looking at still use a lot of energy to get it released. In fact, my group is working on a way of aqueous absorbing carbon dioxide in a way that you can eliminate the energy input. We're so far down by a factor of 100, which is actually good enough. So we're about to submit a paper on that. But I think water absorption of carbon dioxide is a very real possibility. You just got to eliminate the energy penalty. And so the ocean becomes acidic because the absorption of carbon dioxide makes bicarbonates, soda water, slightly acidic. And so that's the acidification of the ocean. So the ocean has other issues. Now, how acidic can it become before the food chain is disrupted? Actually, surprisingly, it can be pretty acidic. I don't do this by computer modeling. I'm just an historian. So you look back at the periods where there were warm periods in the past, it was acidic. And the creatures that are here today were still there. So it's not as though they go extinct. The only real issue is if the transition is too fast, will it have time to evolve? But most of them are microbes, the bottom food chain is microbes, and they can evolve pretty rapidly. So the ocean is got to be part of the solution for sure.
Prof, thank you so much for a great lecture. So, for managing from a soccer group or investment. So the questions and what you described is all about how do we get people to be housed or work in better places or get them from A to B in a faster or more efficient way. And third is how do we put food on the table. Now, around the food element, now you show the graph on the impact of agriculture on the planet. What's your further thoughts on precision fermentations and synthetic biology? My background is I'm a doctor, so I'm a bit biased towards that. Would they develop in a fast enough way to make an impact in the next 10 or 20 years?
The plain breeding part, after we know what we're doing, starting with normal biology with wheat, but with corn, rice, all the main grains, very rapid. And then rapidly deployed because it was more productive, so people get to make more money. Yeah. Harder issue is the fertilizer part, because if you learn anything without fertilizer, you can grow organically without fertilizer if you're very low. But the developing world needs water and fertilizer. And so you need to figure out how to use fertilizer and not end up as N2O emissions. And I outlined two possibilities. You change microbes in the soil so that they can help self-fertilize, or you change microbes in the soil so that the microbes don't turn the nitrates into N2O, or both. And that's essential because without irrigation, without fertilizer, we're 8 billion going 10 billion, 11 billion. It won't be possible. And I might add that in all the things in the world, actually helping the world accelerate to prosperity is a good thing. It doesn't, but you have to do it in a way that doesn't begin to consume the natural resources in a way, for example, the United States does on a per capita basis. That's crazy. But I think we know how to do that. But and it starts with food production and water and drinking water for agriculture. Those two things are really important for raising the wealth of the world. I tried to show in this history lesson. It was the agricultural revolutions that actually led some of the industrial revolutions, and we mustn't forget that.
That's true. Thank you for a good presentation. It seems like nuclear fission technology is one of the proven technologies that we have. So how do we remember how to make them cheaper?
How do we remember how to make them? That's a very good question. Make them cheaper. Well, factory made makes them really cheap. And so you have to make them in a way that you can mass produce them to get down those so-called learning curves. Skeptics say, oh, you don't want just one design because if there's a really fundamental flaw in that one design, then everything's flawed. Yes, but I mean, we do industrialize certain things in that way. So I think, economies of scale, the learning curve is very important. And I still have a lot of hope for small modular reactors of the 50 or 100 megawatt kind. And if you want a half a gigawatt, you just put 5 or 10 of them together. And it could be made very safe. Got to overcome the other inertias, the industrialization. I mean, we look at cars. If you made cars one by one, okay, as Ferrari does, they started at $150,000. If you made a Chevy one by one, it would be $50,000 or $100,000. But mass production enables you to make them and sell them, at a profit at $20,000. So mass production is huge. So if you mass produce these, then there's a real possibility. Uranium, there's ways. Oh, by the way, published paper mining uranium out of seawater also. So I don't think the uranium is the issue. It's learning how to do what we used to know how to do, which is sad.
Hello, my name is Rafael Song. I'm a professor in mechanical engineering at NIL Delhi. I really enjoyed the talk. I think you gave a very beautiful view of this issue. And I think you highlighted the importance of materials, material development, new materials. And one material that I'd like to bring up in this context is superconducting materials. Can this
What materials?
superconducting?
Yes.
Semiconductors. So there was a buzz about room temperature or ambient temperature superconducting materials recently. And I wonder if this could be a really game changer in the energy crisis that we have. The second material they would like to bring up is going to be 2D materials. Using the 2D materials can revolutionize the electronics industry, and we have less energy loss and everything, so we become more efficient and more. So that's sort of my question about these two new materials.
Well, let me start with 2D materials. Yes, I think they have great possibilities, both as 2D and 1D materials. I would call a nanotube a 1D material. Graphene is a 2D material, hexagon boron nitride is a 2D material. There's very real possibility that graphene and hexagon boron nitride conductors and insulators can be something. People are beginning to think of ways of turning this into integrated electronics. Believe it or not, very far away from that, but I'm on an advisory board for Applied Materials, and they're looking 5 and 10 years in the future. Is it possible to use to synthesize in highly integrated ways these 2D materials? Because that is the limit. 1 atomic layer thick of insulator and 1 atomic layer thick of conductors. And so, and your first question was
The superconducting
yes.
material.
Yes, if you could get superconducting material that can carry significant currents, which means high critical fields from magnetic fields, it would be amazing. Right now, the 1.1 megawatt lines that China is building, 3,200 kilometers, they lose about 5% of the electricity from losses. So it's not much, but what superconductors will do is means you don't have to go to super high voltage because you're kind of at the limit now because of corona discharge issues, as well as the sheer size of the channels. The other thing is you can go to underground and undersea cabling, which are limited by dielectric strength to maybe 500, 600 kilovolts at most. And so if you can make really inexpensive undersea cabling that can, I showed you 12 gigawatt. Undersea cabling, as far as I know, is like a half a gigawatt now. So if you can get to these multi-gigawatt then you can lay cables underneath oceans, underneath riverbeds and other things like that, where because you're not going to get as much resistance from overhead lines. People don't like overhead lines. I'm not going to go there, but anyway, they just don't like them. And so it would be revolutionary. It can transform transmission and distribution. And we need all the transmission distribution we can get our hands on. So it would be a very big deal. So unfortunately, it hasn't come to pass yet. At least it doesn't, claims of superconductivity emerge every couple of years, room temperature, and then they disappear. But there's no theoretically impossibility of them, right? Using big energy gap. Energy gap is super good.
I think perhaps,
Okay.
questions, yeah.
Okay.
Okay, thank you so much. Please, read this.
I want to go long.
No, it's good.
Yeah, they. It's inspired. Maybe it's better if you.